Hey everyone, and welcome back to AI.Code.Cast. Today we're taking a deep dive into a problem that's a real brain teaser. And it's one that coding interviewers love to throw at candidates. It's called Furthest Building You Can Reach.
Yeah, it's a really good one because it seems simple at first, but then as you start to think about it, you realize there's a lot of depth to it.
For sure. So to set the scene, imagine you're in a city with a row of buildings, each with a different height. You want to get to the furthest building possible.
Like a parkour challenge almost.
Exactly. Now, you've got two ways to move. You've got bricks, which let you climb one height unit at a time, and you've got ladders, which can take you over any height difference in a single leap.
Right. But here's the catch. You have a limited number of bricks and an even more limited number of ladders.
So the challenge is to figure out the furthest building you can reach using your limited resources.
And the trick is to use those resources strategically. You don't want to just use a ladder for every single jump.
Right, because you might run out of ladders before you reach the really tall buildings.
Exactly. You have to think about the overall terrain, the smaller climbs, and whether we'll have enough bricks to handle those when you run out of ladders.
Okay, so let's start with the most obvious approach, brute force. Could we just try every single combination of bricks and ladders and see what gets us the furthest?
In theory, you could, but imagine you have 100 buildings. The number of possible combinations would be enormous. Your code would take forever to run.
Yeah, that's not going to fly. So
Yeah.
brute force is out. What's wrong with that from like a computer science perspective?
The issue is what we call exponential time complexity. As the input size grows, the time it takes to solve the problem increases exponentially, so it becomes really inefficient.
So we need a smarter approach.
We definitely do.
Any hints?
Sure, think about what we're really trying to do here. We're trying to use our resources efficiently to overcome the height differences between the buildings.
It's kind of a resource management problem.
Exactly. And are there any data structures that come to mind when you think about managing and prioritizing resources?
When I think about prioritizing things, I think about queues, but not just any simple queue.
Right.
It's got to be something that keeps the most important elements
Yeah.
right at the front, something that sorts itself. Could a priority queue work here?
You're on the right track. And when we talk about priority queues, a specific data structure comes to mind. It's like having a really well-organized toolbox where you always know the smallest tool is right there on top.
A min heap.
You got it.
Okay, so let's talk about how a min heap can help us with this problem.
Yeah.
So as we encounter these height differences between the buildings, what do we do with them in the context of a min heap?
So every time you come across a height difference, you add it to your min heap.
Okay,
And the min heap will always keep the smallest height difference at the top.
got it. So as we move through the buildings, the min heap is constantly reorganizing itself, putting the smallest difference right at the front. Now, how do ladders and bricks come into play here?
Okay, so if you have ladders available, you're going to use a ladder for that height difference regardless of the size. But if you are out of ladders, that's when the min heap gets really useful.
So we compare the current height difference to the smallest one in the heap.
Exactly. If the current difference is bigger than the smallest one in the heap, it makes more sense to use a ladder for the bigger one and use bricks for that smaller one that was stored in the heap.
We are essentially swapping them.
Yes. So you're using the min heap to make sure you're not wasting ladders on small climbs where bricks would do. You're always trying to use your ladders for those big, expensive jumps.
Okay, so we're constantly checking if it makes sense to use bricks for an earlier climb, to save a ladder for a potentially bigger climb later on.
You got it. That's the heart of the min heap strategy.
This is making a lot of sense. So the min heap helps us prioritize our ladders and make sure we're using them for the biggest climbs. Can we maybe walk through an example, see how this works in action?
Sure. Let's say our building heights are 4, 2, 7, 6, 9, 14, 12. We have 2 ladders and 4 bricks. Can you walk me through how we'd use the min heap to find the furthest building we can reach?
All right, so we start at building 0 with height 4. The first climb is to building 1 with height 2. So that's a difference of -2.
Good point. We need to think about the differences in height, not just the heights themselves.
Right, so for this first climb, we don't need any resources, right? Because we are going down.
Exactly. No bricks or ladders needed. We can just move to building 1.
All right, so now we're at building 1 with height 2. The next climb is to building 2 with height 7.
Okay, so what's the difference there?
That's a difference of 5, a positive climb. And since we have ladders, we can use 1 for this climb.
All right, so we've used 1 ladder and 0 bricks, but so far so good. What do we do with that climb of 5?
We add it to our min heap.
You got it. It's the only thing in our heap right now. What happens next?
Okay, so the next climb is to building 3 with height 6, a difference of -1. Again, no resources needed because we are going down. Now we are at building 3 with height 6, and the next climb is to building 4 with a height of 9, a difference of 3. We still have a ladder left, so we'll use that.
Right. So we used our second ladder for that climb of 3. What does our min heap look like now?
It has the climb of 5 and the climb of 3 in it with 3 at the top because it's smaller.
Okay, now things are going to get interesting. We're at building 4 with a height of 9, and the next climb is to building 5 with a height of 14, a difference of 5.
And we're out of ladders. So this is where our min heap comes in. We check the top of the heap and see a 3, which is smaller than our current climb of 5.
So what does that tell us?
It means we should have used bricks for that earlier climb of 3 and saved the ladder for this bigger climb of 5.
Exactly. So we're going to use the ladder for this climb of 5, and we're going to replace that 3 in our min heap with a 5 to show that we use bricks for the smaller climb.
So our min heap now has just the climb of 5 in it. And we've used all our ladders. We've also used up 3 bricks for that climb of 3 earlier. So we only have 1 brick left.
Right. What happens next?
We are now at building 5 with a height of 14, and the next climb is to building 6 with a height of 12. That's a difference of -2. So we don't need any resources. We are going down.
Okay, and now for the final climb.
We are at building 6 with a height of 12, and the last building, building 7, also has a height of 12. 0 difference. So no resources needed.
All right, so we made it to the last building.
That was awesome. The min heap really helped us out there. It made sure we used our ladders for the biggest climbs. We were able to reach the furthest building. I can see how this approach is much more efficient than just trying every combination.
Right. Remember we were talking about time complexity before?
Yeah.
Well, the brute force approach has exponential time complexity, but the min heap approach has a time complexity of n log L.
And log L. Remind me what that means again.
So n is the number of buildings, and L is the number of ladders. Basically, it means that as the number of buildings increases, the time it takes to solve the problem grows much slower than with the brute force approach.
So it's way more efficient.
Much more. And it scales much better to larger problems. And the space complexity, the amount of memory the algorithm uses, is OL, which means it uses space proportional to the number of ladders. This is because the maximum size of our min heap is determined by the number of ladders we have.
That makes sense. So this min heap approach is a clear winner in terms of efficiency.
It is.
But I remember you saying there are other ways to solve this problem. What if we wanted to try a different approach, maybe something that involves searching for a value, like in a sorted array?
You're thinking along the right lines. We can actually use binary search to solve this problem.
Binary search for buildings. That sounds really interesting. I'm all ears.
It is. And it might not be the most obvious solution,
Yeah.
but it's a really clever way to approach the problem.
Okay, so binary search for finding the furthest building. It sounds kind of counterintuitive. I mean, binary search is all about finding a specific value in a sorted list, right? But we're dealing with building heights and ladders and bricks.
Right, but that's what's so cool about this approach. It uses a really clever insight about the problem. If we can reach a certain building, let's say building number 10,
Okay.
then we can definitely reach any building before it, like building 1 through 9, using some combination of our bricks and ladders.
Yeah, that makes sense.
Mm.
So even though the building heights themselves aren't sorted, there's still this order to the problem. The reachability of the buildings has a sort of sorted property.
Exactly. And that's where binary search comes in. We're not going to perform the binary search on the building heights themselves, but on the indices of the buildings.
The indices.
Mm.
Okay, so instead of asking, can we reach this height,
Mm-hmm.
we're asking, can we reach this building index?
Mm.
I'm starting to see it now. So how do we actually apply binary search here?
So our search space is going to be the range of building indices from 0 to the last building. And like any binary search, we start in the middle. We take the middle index, let's call it mid, and we ask, can we reach this building index using our bricks and ladders?
And to answer that question, we would need a helper function.
Exactly.
That takes the building index, the building heights, the number of bricks and ladders, and figures out if it's possible to reach that building. What would that helper function look like?
So this helper function, it's going to calculate the height differences between consecutive buildings up to that target index, and then it's going to sort these differences and try to allocate bricks and ladders to them. If it's possible to reach that index with the given resources, it'll return true, otherwise false.
Okay, so let's say our helper function tells us, yes, we can reach the building at index mid. What do we do next in our binary search?
That means we can eliminate all the buildings before mid because we know we can reach them too. So we shift our search to the right, towards the later buildings.
And if we can't reach the building at index mid,
Then we know the furthest building must be somewhere before it, so we shift our search to the left.
okay, so we keep having our search space until we zero in on that furthest building index. Just like a regular binary search. This is so clever. I never would have thought of using binary search this way. But I have a question. Why do we need to sort the height differences in the helper function? Wouldn't that add extra time to our solution?
You're right, sorting does add some overhead, but it's really important for allocating our lighters efficiently. By sorting the differences, we can quickly figure out the largest climbs and make sure we use ladders for those. We want to save our bricks for the smaller climbs.
Ah, so the sorting step helps us use our resources strategically, just like we did with the min-heap approach, making sure we're not wasting ladders on small climbs. Okay, so what about the time complexity for this binary search approach? It seems a bit more complex to analyze than the min-heap.
Yeah, it is a bit trickier. The binary search itself gives us a time complexity of O log n, where n is the number of buildings. But inside the binary search, we are calling that helper function, which sorts the height differences. And that sorting takes O(n log n time.
So is the overall time complexity O(n log n log n?
That's right, it's O log n from the binary search multiplied by O(n log n from the sorting.
And how about space complexity?
That's going to be O(n), because our helper function might need to store all the height differences in a list in order to sort them.
Okay, so this binary search approach, it's super elegant, but maybe not as efficient as the min-heap approach, especially if we have a lot more buildings than ladders.
Yeah, that's a good observation. It really depends on the specific situation.
But it's still a really cool solution, and it shows how we can think about the problem in a different way.
Exactly. Now, remember how we used a min heap before to keep track of the smallest climbs so we could use bricks for those? Well, we can actually use a max heap to focus on the biggest climbs instead.
A max heap. So we are flipping the script.
We are. With a max heap, we are basically going to use a greedy approach. We'll try to use bricks for as many climbs as we can and only use a ladder when we absolutely have to, for those really big climbs.
So we're assuming that we'll have enough bricks to handle most of the smaller climbs.
Exactly. We're betting that the smaller climbs won't drain our brick supply too quickly, so we can save the ladders for those big jumps.
Okay, I get it. So how does the max heap actually help us make those decisions?
So we start with an empty max heap, and as we encounter each climb, we add it to the heap. And here's the important part. We add all climbs to the max heap, regardless of whether we use bricks or a ladder.
Interesting. So the max heap is keeping track of every climb we've come across, with the largest one at the top. I bet this comes in handy when we run out of bricks.
You got it. As we add each climb, we subtract its height from our total brick count. If we still have bricks left, we can move on to the next building, but if we don't have enough bricks for the next climb.
Then we check our max heap.
Exactly. We look at the top of the heap, which is the largest climb we've seen so far. If we still have ladders left, we can use a ladder for that climb.
Oh, so it's like we're going back in time and saying, hey, should have used a ladder for that one.
Exactly. We take that largest climb off the heap and we add its height back to our brick count because we are now using a ladder for it.
I love how this max heap allows us to dynamically adjust our strategy as we go. So what's the time complexity for this approach?
It's going to be O(n log n, because in the worst case, we might add all n climbs to the heap and then remove them all. And both adding and removing from a max heap takes logarithmic time.
And space complexity.
Also O(n), since our max heap could potentially hold all the climbs.
Okay, so the max heap has the same time and space complexity as the binary search approach. But how does it compare to the min heap?
Well, the min heap with its O(n log L time complexity can be more efficient, especially if we don't have many ladders. But really, both heap approaches have their pros and cons, and they give us different ways of thinking about the problem.
This has been such an awesome deep dive. We've explored 3 different ways to solve this problem, each with its own unique twist. It's amazing how something that seems so simple at first can have so many different solutions.
Right. And each approach gives us a new perspective on the problem, whether it's efficient resource management, leveraging the problem's inherent order, or using a greedy approach with some dynamic adjustments. There's no single best way. It all depends on what we're trying to optimize for.
Absolutely. Well, folks, that's all the time we have for today's deep dive into the furthest building you can reach problem. We've explored min heaps, binary search, and max heaps, and we've seen how different algorithms and data structures can be used to tackle the same challenge. Hopefully, this has given you some new tools and insights to use in your own coding journey. Until next time, keep on coding, and we'll see you on the next AI Codecast.